standard. And after that, there are many revisions, basically many other versions of IO 2.11. All right, so if we're talking about security, we'll think about authentication, right? So who can have access to the network? And the other aspect we think about is how to protect data. That means what kind of encryption that you do in order to protect data at the medium access control layer, okay? So in a wireless LAN, so usually controlling access is done by limiting a device access to the access point. So this is the simplest scheme, right? We'll talk about the simplest one. And only devices that are authorized can connect to the access point. So this is the principle, and this is the principle that we still use today, right? With the evolution from WEP to WPA to WPA2. And the simplest way is to use MAC address filtering, right? So, so this is one example of the architecture of a wireless local area network. This is the local area network, and we have an access point connected to it, and we have the laptops connected to the access point, right? And this is how we do MAC address filtering. So let me make this space bigger a bit so I can see it easier. So when they configure a wireless router or access point, they can specify the devices that need to be kept away from this router, no access, and only let these devices in, right? So they have permit only or prevent. Okay, so that is the, sorry. Okay, right? So that is MAC address filtering. And this is another example. And this is what we've been doing so far. We have a service access ID, and then we must have a key, right? So this is the Wi-Fi key, okay. So that's what we've been doing with access to wireless local area networks. Okay, so the problem with MAC address filtering is that the addresses are transmitted in the clear. There's no encryption. So an attacker can just sniff the MAC address, right? And then use that address, change the address in their devices and access to the network. And again, to filter addresses, you need to manage a large number of MAC addresses, and that could become very difficult. And address filtering does not provide temporary access to a guest user, because now you need to manually add the user's MAC address into the access point. So it's not very convenient, it's not scalable, right? So that's why this simple approach is was just one very simple way. But the first security protocol tried to overcome some of those challenges, and it's called wide equivalent privacy. This is the very first security protocol for wireless LAN. Okay. And from the name here, you can see that it's tried to copy features of security in wired networks to wireless network. And obviously, some of them may not work very well, and we'll see later. Okay. All right. So, so with WEP, the goal is to ensure that only authorized people can view the wireless information. All right. And the WEP uses encryption to protect the traffic. And it was designed to be efficient and reasonably strong. Now, this may not be true anymore. Okay. Sorry.
Call from 6474.
All right. So now let's talk about how WEP authenticate users and then how it can protect traffic. So WEP keys are secret keys that can be 64 to 128 bits long. And the access point or the devices each can hold up to 4 shared secret keys, all right? And for example, each of them can have 4 shared secret keys installed with the device itself. And one key can be designated as the default key, right? Okay, so device authentication is done using one of the 2 types, either open system authentication, lets everyone in, or shared key authentication. Only the computers that know the shared key can get in, right? Okay, so this is open system authentication. So basically this is, you can consider this as a free Wi-Fi. When you go to a public place and you can get in the network, it's open system authentication. The last laptop, the device send a message to the access point saying that I need to connect to SSID, service set ID bill, basically this access point. And then the access point say you are authenticated, respond with an association response frame, say you are authenticated, and give this laptop the access to the network, right? So this is basically free Wi-Fi that you use, let's say in shopping malls and in store. So this is open system authentication. Now, this is shared key authentication. So with shared key authentication, it involves a set of steps, and it involves a challenge from the access point. So first, when a laptop wants to join a network, it sends a message to the access point saying that I want to be authenticated. And the access point send back a message to the laptop, which is a message, all right? Now the message changes every time. It's not just the same message here, but it's the message. And this is called challenge text, all right? Now the access point and the laptop shares a key. They both share a key, right? And the laptop, before it can access the access point, it must know that key. It just as the concept is analogous or equivalent to the concept that before you want to access a network, you must know the password, right? It's not the same, but this is a concept. The laptop knows the share key. So the laptop encrypts this text with the key, with the share key. And this is the encrypted text is sent to the access point. Now, because the key is shared, the access point knows the key as well. It does the same thing. It encrypts this message using the same key. And then it compares the 2 encrypted messages. If they match, that means the laptop has the share key, right? And if the laptop has the share key, that means the laptop has been given authorization to access this network. So in that case, the access point send back an authentication frame to the device saying that, yes, you are given access to the network. Okay, so that's the main idea, right? Now the detail of the exact messages exchanged, we're not concerned with those messages. We just know this is the process of getting authenticated with the share key, all right? All right, so this is the authentication, all right? Now, let's talk about data protection, which is encryption, all right? So this is different. This is to give the laptop access to the network. Now, when the laptop and the access point exchange data, exchange messages or frames or packets, those must be encrypted so that other people cannot get and then read the message, right? Okay, so, and this is the encryption process. Now, when a station has a packet to send or frame to send, it first generates the cyclic redundancy check for this frame as an integrity check value. Okay, so what is a CRC, cyclic redundancy check? All right, so this is just to remind you of this process. Okay. All right, so this is cyclic redundancy check. Now, just a question. I assume that you learned this in 3213, right? Who has not seen this before? If you have not seen it, just type no on the chat window if you have not seen it. All right, so the other way, right? If you have seen this before, type yes in the chat window. If you have seen this before. So do you know what cyclic redundancy check is? Anyone? Only one person, two, three. Okay, so one sound familiar, one forgot. Okay. How about the rest? Okay. All right, so that means you must have learned this in a previous network course, right? So, okay, it's very simple. You can Google search cyclic redundancy check, and then you get the information from Google, and then you can review it. If you took 3213, you must have seen this before. The main idea of CRC here is just very simple. You have a frame to send, a frame of data to send, right? So let's say this is a data 1101011011, and then you perform an operation. At the end, you get this one here is called CRC, the cyclic redundancy check code. You will concatenate the message, the data with this CRC and send to the receiver. When the receiver receives this message, he or she will take the data, perform the same operation. It should get the same CRC. If it gets the same CRC, what it means is the message has not been changed. The message has not been tampered with. That's why the receiver can get back the same CRC, all right? And that's the purpose of the CRC, to make sure that the message was not changed, was not tampered with during transition, okay? So that's the purpose of the CRC, all right? Okay, so the station will generate the CRC, right? And this is called an integrity check value, ICV, okay? Right, so let's see here, right? So it will go through the CRC algorithm, and then it have an the remainder. If you take a look at this, that should be the ICV here in this example, all right? At the end, 1110. That should be this ICV here. That's the CRC code, okay? All right, so that's the first step, okay? Now, in the second step, it will generate something called an initialization vector on IV, right? And then it concatenates the IV with the secret key. Basically, the WEP key share with the access point. And then it applies RC4. So RC4 is an algorithm. Okay, it's an algorithm. And when it applies RC4 to the IV and the secret key, it will create an RC4 key stream. All right. Basically, it's a sequence of 0 and 1, and it serves as a key, right? It's a sequence of 0 and 1, but it serves as a key. Okay. So we take the IV, it generates an IV, concatenates with the secret key, go through an algorithm called RC4. Okay. This is RC4. Okay, RC4. All right. And that's produce a key stream. Okay. RC4 is an algorithm that generates a random stream of bits. Okay. And then basically it's a sequence of bits 1 and 0, 1 and 0, but it serves as a key, right? It works as a key. And then now you have a key stream and you have a string. Basically, a key stream is a string of 101001. Okay. The text and ICV also a sequence of 1 and 0 bits, right? Now you perform XOR, exclusive or XOR on these. all right? After you perform this, you get something called ciphertext. So basically this here becomes ciphertext, all right? And then the sender will append the IV or concatenate the IV with the ciphertext and send to the receiver. Okay, now ciphertext means the text that has been encrypted. Okay, and the text that has not been encrypted, we call it plain text. All right, so you can imagine the key stream here as a key, right? As a key, a secret key. But instead of being a key itself, it's a stream of 0 and 1 bits. Okay, so this is the process. Yeah, it appends the IV to the ciphertext and transmits to the receiver. Okay, right, and this is a review of CRC. Okay, so you should review CRC. So again, the same process here. Oh, so this is random. This is CRC. This is pseudo random number generator. P pseudo random number generator. Okay, RC4 is an algorithm that generates a pseudo random number, or a number basically, or a stream of 0 and 1 bits. Okay, pseudo random. So I'll just write here PRNG, pseudo random number generator. All right, so RC4 is one of those algorithm. Okay, all right. Okay. And here we repeat, we have the IV, we have the initializer vector and the secret key. We concatenate them, run through RC4, have a key stream, right? A key stream basically is a sequence of 0 and 1. And then we have the plain text. And remember, the plain text, we would need to have the CRC code here as well, right? To make sure that the receiver can check for integrity. And then we do XOR and we get the ciphertext and we send to the receiver, okay? All right, so again, the process here, I will, the process here now. The IV and the share secret key, right? So this arrow should be here, share secret key. Both of them concatenated, run through RC4, have a key stream, right? And then the text and the CRC, right? The RCRC is here, is concatenated as well. We perform XOR here. We get the ciphertext, and then we add the IV here, and we send this to the receiver. So the receiver will receive the IV and the ciphertext, right? Now, the receiver has the share secret key, right? So this key is shared by both of them. It will run the IV and the share secret key, right? Remember, the IV share secret key through RC4. It gets the key stream, right? Now from the key stream, it gets the ciphertext here and perform XOR again. And it will get back the original text and the CRC value. It will use the CRC value here to check the text here to make sure that there's no changes. There was no changes to the text while in transit, right? So again, the receiver takes the IV because the IV was sent here, and the share secret key, run them, concatenate them, run through RC4, get the key stream, get the ciphertext here, run XOR, get back the original text and the CRC, uses the CRC to check for the integrity of the plain text here, right? Any question? Now the math behind this is complex, but we're not going through the math. We just learn the algorithm only, right? But if you want to know the actual math, you can do a search on there's so much information about the math behind this kind of encryption, decryption. Okay, so but we're not concerned with the math here. All right, so WEP is very sensitive to the network noise, right? So Sharam asked a question. When you say that, you mean if there's a change? Yes, that's right. In this here, this part here, the text and the RCRC, the ciphertext here, if just one bit is flipped, right? If one bit is flipped because you have noise, then of course you get back the text here. It will be wrong because one bit is flipped. And if you apply the CRC, it will not match because the CRC, the algorithm will think that the text has been changed, right? That's true. WEP is very sensitive to the network noise because only if one bit is flipped, it will destroy or ruin the whole text here because the CRC here doesn't work with this text. Yeah, you're right. Okay. All right. So now we analyze the robustness of WEP encryption. Okay, so the IV is 24-bit long. So there are 2 to 24 choices, right? So the IV, remember the IV is used here, right? The IV is used here, okay? And for every frame, we must have a new IV, right? So for every frame that the sender sends, it must have a new IV, okay? Right, so so there are only 2 to the power 24 choices. So the probability of choosing the same IV value is more than 99% after about 1200 frames, okay? After 1200 frames. And then if you have 1200 frames and then the chance of repeating the same IV is 99%. What it means is only a few minutes elapse with 11 megabits per second and 1 kilobyte frame size. Okay, so just sit down and do some math and you can see that's only a few minutes and then you have to repeat the same IV again. And the reuse of IV within a few minutes is very dangerous. So we'll see an example very soon. Okay. From where we get this IV? Oh, this IV is you just get a number from 0 to 2 to the power 24. Okay, you get a number. So let's say for the first frame, you use 0 and then 1 and then 2 and then 3 up to 2 to the power 24. But with this IV here, 2 to the power 24 may seem big here. But remember, if you use very high speed and 1 kilobyte frame size, and this fact here, only a few minutes will elapse when you have to reuse the same IV again. Okay, so later when we have time, I will show the math, but the main idea here is only a few minutes elapse when you have to reuse the same IV. So that's one problem. And the IV value are sent in plain text. Okay, remember here, the ciphertext, yes, it's encrypted, but the IV we send in plain text here, no encryption of the IV. And if this happens, attackers can detect a duplicate value and we use passkeys in order to decrypt future messages, all right? And this is one example. Okay. All right, so in this example, the security problem is caused by this. We have 24-bit IV, and every time we send a frame, we have to use a new IV. So the IVs will eventually be reused. So, and the IV transmitted in plain text. So what it means is the IV reuse can be detected, right? So that means if the sender reuses that IV, an attacker knows immediately that the IV is reused. And this will cause problem, all right? So this is one example. So Trudy is the attacker, right? Alice is a person in the network. So Trudy will, now first I have to emphasize, this scenario is in theory, all right, in theory. Basically, this is a worst case scenario, right? In theory, it may not happen in real life, but this is a theoretical case. It can happen in the worst case scenario. From a security point of view, if you have a successful attack, even in theory, even in the worst case scenario, that security protocol or algorithm is not considered secure because someone would exploit it, all right? Just to make sure that, because you may think, oh, this may not happen. Yes, this may not happen, but in security, if a theoretical situation can happen, that implies that that protocol or algorithm is not secure, all right? All right, so basically Trudy will make Alice encrypt known plain text, right? So basically Trudy make Alice send D1, D2, and D3 and D4, all right? Now, like I said, this may not easy to be done in real life, because how can you make a person send known plain text? It could be, for example, you send an email to a friend, right? So let's say you are Trudy and Alice is your friend. You send an email to your friend, tell your friend, can you please email me the handout from the assignment handout from this course, right? So in that sense, you forces your friend to send you plain text that you already know, because you know the handout of the assignment, right? Yeah. So that would be one scenario. But that's what it means by Trudy causes Alice to send known plain text, right? D1, D2, D3, D4, right? And remember, this is plain text, right? So D here is in this. So we have three variables, C, CI, DI, and KI, right? With IV here. I stand for the message here, D1, D2, D3, right? D is the plain text, C is the ciphertext, and K is the key stream, right? Remember when we have this, we have hit this here, maybe this one. So this is the plain text, right? So this should be D, right? D here. This is KI, DI. XOR together, we get CI, okay? All right. So DI XOR with KI, we get CI, okay? Now, Trudy knows DI and CI, right? Because when Alice sends DI, that Trudy already know DI, and then it's CIs, right? So Trudy knows CI and DI. So assume we just think about one only, right? D1. So C1 and D1. And from that, Trudy can compute K1, okay? Can compute K1. So now Trudy will know K1, K2, K3, right? For the value IV here. The next time IV is used, Trudy can use this information to decrypt the message, all right? So I can give you a very simple example to illustrate how this can be done. All right, so now this is very simple example. Let me stop share the other one, and I share this, the new screen. Okay, and then make it a bit bigger. Okay, and I'll share this one here. Okay, all right, so remember we have DI, KI, and right? So basically we have DI XOR with KI to get the ciphertext CI, right? This is a very simple example. Assume that the plain text is attack, D1, D2 is stay, D3 is retreat, right? In practice, you have a longer message, but in this example, I use a very simple example. Let's say attack, stay, and retreat, they are the message, right? Messages. And then assume this is the key stream, right? And from this, I get the ciphertext here. All right, I get the ciphertext here. So, and this is the IB, right? Now at 9 o'clock, Trudy asked Alice to send attack, this message attack, right? And then this is the ciphertext. So Alice will store these. Alice will store all of these, right? Basically, these three messages and these three key streams. Okay, so it will be stored by Alice. Now, at this point, Trudy and Alice are friends. They are friends. So that's why Trudy asked Alice to send these messages and then can get these key stream and these ciphertext. Now, at 10 o'clock, they become enemies, right? At 10 o'clock, they become enemies. So now, Trudy now can listen to the messages, and because the IB is sent in plain text, so whenever Trudy sees a message, a ciphertext with the same IB, Trudy will store the ciphertext. Trudy will store the KI, right? And remember, Trudy already has this in her computer. If I see this ciphertext and I know that this ciphertext go with this IB, will have this key stream, right? So now what I need to do is apply XOR to these so I can get back the message here. So now Trudy know that the message from Alice is attack. All right. So every time the IB is repeated, Trudy knows that, yes, I have this key stream for this IB. I have this ciphertext for this IB. If I combine them, I get back the original message. All right. This is a very, very simple illustration of the example we just talked about before. All right. Any question about this? Okay. All right. So let me stop share here. So basically, Trudy will save this information. Okay. Of course, there would be many, many messages in order for you to get enough vocabulary to detect future message decrypt. Okay. When was IB shared? Okay. IB is shared here. Let me get the IB is shared here. Okay, the IB is shared. Sorry, I have to stop share the other one and then share again. Okay, the IB is shared here. When the sender sends the ciphertext, it appends the IB to the ciphertext and send it to the receiver, right? Anyone can hear this IB, including the receiver, Trudy. So Trudy gets this IB. Okay, the IB is shared there. All right, any question about this? Okay. Sorry, let me try to move it here. Okay. All right, so the problem here is IB can be repeated very often and it's sent in plain text. That's the problem, causing this kind of attack. Okay. All right, so now we've seen authentication, right? Authentication is open system or shared key authentication. And data can be encrypted using the encryption process we just talked about. And each packet requires a new IB. And the IB can be repeated very often. And then at that point, the attackers can exploit that in order to decrypt future messages with the same IB. Okay. And another weakness of WEP is the key is static, right? No periodic updates. And that is a very, very bad security practice. You have to update the key very frequently, right? The CRC is weak in integrity check. An attacker can flip a bit in the encrypted data and then change the CRC as well. And as we said before as well, it's sensitive to noise for the same problem. Only one bit can be flipped, and then you have to throw away the whole frame. And authentication is too simple, all right? And because WEP is not very strong the next step is to make something better, and that's when WPA was created. Okay, so WPA stands for Wi-Fi Protected Access. Okay. Right, so this is a bit of history of WPA. In the 80s, we had something called Wireless Ethernet Compatibility Alliance, WIGA, and it's a group of wireless equipment manufacturers and software providers working together to create Wi-Fi, wireless Ethernet technology equipment. And the goal of this group is to encourage wireless manufacturers to use AO2.11 technology, basically to use the standard so that all equipment is compatible, and to promote and market these technologies, and to test and certify products based on this the AO2.11 standards to make sure that products are compatible, right? In 2002, they changed the name to Wi-Fi Wireless Fidelity Alliance. And in 2003, they introduced WPA. Okay? So WPA was intended to protect both present and future devices. And it addresses both authentication and encryption, right? Authentication is done using PSK or AO2.1x, sorry, not 11, 0.1x, and TKIP is used for encryption, right? So we'll go through this later, yeah, now, yeah. All right, so let me see here, okay. So WAP improve WEP encryption. Remember we said before about the attack scenario between Trudy and Alex. This is when WAP is trying to do improve the encryption. So this key size is increased to 128 bits instead of 64 bits. The IV was 24 bits, now it's 48 bits. The security keys will be changed periodically using temporary key integrity protocol. And encryption keys are changed based on a master key after a certain number of packets have been sent, right? Remember with WEP, the key is static. We never change it. Now the keys are updated periodically. An IV is mixed with data and not concatenate, right? So if it mixes, it's harder to extract the IV from the frame. The ciphering scheme is the same as WEP so that it can be compatible with old wireless LAN cards, okay? Right, so WPA uses a new message integrity check called MICO, right? So it doesn't use CRC anymore. It's called something called MICO. And it adds a frame counter to MICO to avoid replay or forgery attack, okay? Now forgery attack means the message is changed, right? It's modified. Replay attack, anyone know what replay attack is? Anyone know what a replay attack is? Okay, so replay attack, right? Send the same frame to the router or to another party, right? You send the same frame. So what it happens in some authentication scheme, for example, let's say, you know, in the old day, in spy movies, you have one person knock on the door of another person, and the homeowner asks, what's the password, right? And the guest say the password, then the owner opens the door. Now, if someone is hiding nearby and hear the password, the spy, that person later comes to the house, knocks on the door, and the owner would ask, what's the password? And the spy say the same password, right? And the owner opens. That's replay attack. You have the same message, you replay it. In this case, the spy replay the password in order to get access to the house, right? So that's replay attack. So we add a frame counter to avoid a replay attack. So if you have a counter, when the counter, let's say the original frame has a counter of 10. If the sender receive a counter of 10, it would expect the next message with the same content would have a counter of 11, right? Not 10 anymore. So that means an attacker cannot replay the same frame, right? It cannot just replay the same frame with the same counter, because the person who received the message would know that that was an old message because the counter has not been changed. The counter should have been 11 and not 10, right? Okay. All right. So, so this is the overall frame format. We'll go into detail later, but the format here shows this is the AO2.11 format. This green part contains information related to AO2.11 medium access control. For example, we've seen before the address of the sender, address of the receiver, different kind, the duration of the frame, for example. And then this part is the header for AO2.11i. Basically, it contains security information. And you can see here, the security information here would be the IV, right? This is now the IV. And the IV now is used as the frame counter or the frame sequence to defeat replay attack, as I said before. And there's a key here. It put here key ID, so we'll see this later. And then we have data, right? And then we have message integrity code. So this one plays the role of CRC as before, but CRC is so simple, it's too simple. Now they have something more complex, more sophisticated, and it's called Message Integrity Code, MIC, and they call it MICO, all right? So MIC or MICO here, the code, this code here is used to ensure the integrity of everything from here to here, all right, from here to here. So the MIC is used to ensure integrity of this part, right? So if you think about this as the CRC, then it's used to ensure the integrity of this part here. That means no one has changed or tampered with this part. And then you have the frame check sequence. So this frame check sequence is for the whole frame, all right, for everything, for the MIC as well. Remember, the MIC is to ensure the integrity of this part, right? But what can ensure the integrity of the MIC, right? What if someone changes here? That's the role of the frame check sequence. It will ensure the integrity of everything here, okay, of everything here, all right? So that's why we have a stronger, how can I say, mechanism to ensure that the message is not changed or tampered with, okay, right? All right, so let's talk about authentication. So authentication, WPA has two options, PSK, pre-share key, and it's inexpensive. It's used for home and personal networking. And the other option, the second option is AO2.1X. It's more expensive because it's more complex, more secure. And it's used for enterprise networking, for companies, for big offices, for big companies, big organizations. Okay. All right, so pre-share key first, PSK first. It's called PWA, personal security. So it uses a passphrase to generate the encryption key. Okay. And the key must be entered into both the access point and all wireless devices before the devices can communicate with the access point. Okay. And the PSK is not used for encryption. All right. So this is the another principle of security. The other principle we talked about before, you have to update a key regularly, right? You have to update a key regularly, because if you keep it too long, it will give attacker time to crack your key. So that's why you have to keep changing it. The second principle of security is don't use the same key for multiple purposes. All right. Each key has its own purpose. For example, you must have a key to the front door, another key to the back door, another key to the side door. You should not use the same key for 3 doors, right? So it's the same concept here. You use the PSK for authentication, right? If it's used for authentication, then it should not be used for encryption, okay? So for encryption, we can use a PSK to generate a set of keys, all right? To generate a set of keys in order to use for encryption, okay? So if you use PSK and generate another key, so this key is called a pairwise master key, PMK, all right? And then after the PMK is generated, the access point and the device use a 4-way handshake algorithm to create more keys, right? To handle key management and distribution. That means to use more keys, to create more keys for encrypting data and for other purposes as well, as we'll see later. So the 4-way handshake is used to create keys, manage keys, and distribute keys, all right? Okay, so this is WPA personal security. So SOHO stands for small office, home office, small office, home office, okay? So in step 1, we have to enter matching password into the access point and the client or the laptop, okay? They must have the same password. So you can imagine as a password for your Wi-Fi. So, and then when a client wants to join the network, the AP checks if the client password matches the password that it has in the system. If so, if this is a match, then it lets the client in. Otherwise, it will reject the request and does not let the client or the laptop join the network. And then after that, they will go through a 4-way handshake to generate keys, right? And the keys are delivered and installed on both the client and the access point for them to exchange encrypted data, okay? Okay, so let's see. Matthew has a question. There is more overhead for each frame compared to WEP. Yes, of course, there is more overhead during the process of authentication and the 4-way handshake compared with WEP. You will see later, yes, there are more frames during the process, okay? But then that's why it's more secure, all right? Compared with WEP, yes, it's more overhead, it's more frames to exchange, but that's why it's more secure, okay? All right. Now, the witness of PSK is a 64-bit hexadecimal number and usually generated from a passphrase. Then the passphrase consists of letters, digits, punctuation between 8 and 63 characters in length. And as with any kind of password, if it is a common word, it can be easily attacked with something called a dictionary attack, right? So, so you know that if they use a very common keyword or password for the passphrase, let's say password. I think another one is princess. Another one is 1, 2, 3, 4, 5. So these can be cracked very easily by attackers, by hackers, right? So that's the weakness, because if the passphrase is not chosen carefully, it can be attacked. Another problem is people may send the key by email or another insecure method. So you can imagine this as the password to your Wi-Fi network, right? If you send that password to someone and your email is intercepted, then other people will know the password and will use your Wi-Fi network. Changing the PSK is difficult because you must type new key on every wireless device and on the access points. So you notice every time you change the password on your access point, you have to change the password on every device that uses that access point. So we've seen this before. And in order to allow a guest to use your access point, you have to give the key to the guest, right? So the same as what we've seen now. All right, so now authentication. Authentication has three components. Now it needs, in addition to the access point and the client, right? It will need a server, okay? It will need a server. So you can see already that is more complex than WEP. With WEP, we don't need a server. Here we need a server, and this server is called Radius, Remote Authentication Dial-in User Service. Okay, and it uses EAP authentication framework. EAP stands for Extensible Authentication Protocol, and it is a framework. What it means is it provides only the architecture, the main idea for the authentication, an authentication protocol, but it does not provide the actual implementation details. So that's why there are many implementations of AEP. Right, and one of it is EAP TLS, which is what used in AO2.11, and we'll go through this. We're not concerned with these. All right, I just list them as example. Okay, so EAP TLS stands for Transport Layer Security, and this is what used in AO2.11 security, and this will result in, after the authentication, it will produce a key called pairwise master key, right? PMK. And then the access point and the client or the laptop will follow a four-way handshake protocol in order to create more keys and to manage keys and to distribute these keys, right? So it used PMK to generate a pairwise transition key. Okay, so we'll see that later, how they can generate the key. All right, so let me see here. Okay, so I think we'll cover this slide and then we'll save the keys part for the next lecture, because it's kind of complex. So I don't want you to, so it's late, so you may not be able to absorb everything. So just try to focus on this first. Yeah. Okay, so let me make it bigger so it's easier to see. Yeah. So remember we said now we need a server, right? We have the client and access point as before, but now we need a server as well. And both of them must have connection to the server. And we have something called certificate authority. Okay, so certificate authority provides certificates to each device in order to certify that this is a trusted device. All right, this is used for public key encryption. We're not cover public key encryption in here, but you can consider the certificate here as the proof of trust. That means it shows that the client, if the client has a certificate and it shows it to the authority or to the access point, it shows that this client can be trusted. Okay, so you can consider the certificate in that sense. All right, so in EAP TLS, first, the client will send a request to the access point asking for authorization to join the network, right? Now, at this point, the access point will block all other requests until authentication completes, right? So this is for efficiency. You just solve one problem first to authenticate this person, to let this person in, right? So now the access point send back a message to the client asking for identity. Who are you? All right. So the client will provide the identity to the access point. Okay. And then the access point will send this information to the server and to the authority. Basically, these entities will help verify the identity of the laptop. Okay. And then after the server and the authority verifies the identity, it will send back a server certificate to the client. So basically, the server tells the client that, yes, you can trust me. All right, the certificate say that, yes, you can trust me, because, you know, sometimes attacker may set up a server to gather information, to do all the bad things to laptops, right? Trying to connect to an access point. And the client also send a certificate back to the server saying that, yes, you can trust me as well. I've been certified, right? So this is the process, very high level idea of the process of authentication. Okay. Now, now the server and the access point and the client, they will exchange messages in order to generate keys, right? So these keys will be used for encrypting data, decrypting data, all right? And after having these keys, the access point also send the broadcast key to the client as well. All right. So these keys are used for single messages, single one-to-one communication, unicast communication. But sometimes the access point broadcast or multicast messages, it needs a key as well. And this key is sent after this using one of these keys here. All right. Okay. So I think we stop here, right? So this is the authentication process. And this is the key generation process, all right? So the second part here, key generation process. And next time we'll talk about the key generation process, key management, generation, management, and distribution, right? Okay, so any question?